So now that we saw how we can prepare our dataset for the bag of words model, let's actually go ahead and train a bag of words classifier. And now we are here at the second part, training a logistic regression classifier, where we will inherit all the code that we prepared in the previous video. So essentially this is all the same stuff that we did already, where we loaded the dataset, we partitioned the dataset into the training, validation, and test subsections, and then we use the count vectorizer here to transform the feature vectors or the text into bag of words feature vectors. So that's what we've done in the last video. So now we are going to define a data loader so that we can then sample the data efficiently for our model training. So let's start by defining the data loader here. So for that, we are going to use a custom dataset class. We will create that one using, of course, our familiar dataset and data loader classes from Torch Utils data. And here the new class, let's call that text dataset, will inherit from the Torch dataset. Of course, we need our init method, and we always have to have a self for each method. And this will get the matrix, the feature matrix, along with the class labels. So the class labels will be a vector or an array. Oops. Didn't mean to execute that yet. Let's keep typing here. So we will instantiate our features, which is a Torch tensor. So before everything was a NumPy, so we have to convert that to a Torch tensor. And for features, we usually prefer to have a d-type of float 32, as we discussed in a previous lecture. Then for the labels, we do something similar. We do torch.tensor on the label array, but now we want integers. So we use torch int 64, and then we return both. Actually, no, we don't need to return anything here because we are just in the constructor method still. So the next method we need is a get item method. So this will yield one data point at a time from our arrays that we defined above. So we will need an index, which is used by the data loader later. So we define the features and we yield one feature vector using the index, and we do the same thing for the label. And then we return this feature vector along with the class label. And then also, of course, the length method. So we call that len. It's a convention in Python or PyTorch here. And we return this as, we can choose either or. We can use the labels or we could use the features, but let's just use the labels here. The first dimension would be the size of that dataset, the number of entries. And then we can instantiate our train dataset. Remember, we need the two dense because we have a sparse matrix for xtrain. And what we do here is we need the class labels. So let's return them. It might work as a pandas series, but I'm not sure. So let's just use NumPy. So when we do values on a series or data frame object, this will return the underlying NumPy array. And then we are going to instantiate the train loader. So we need a data loader here, which wraps our data set. Call it train ds, and let's use a batch size of 32. And we, of course, want to shuffle. And this is it. That's all we need for now. We could actually use multiple workers here, but this is such a small, simple data set. And that's quite okay if we do it like that, because we are going to train a very simple model anyway. We want to do the same thing for the validation set and the test set. So just to make sure everything works okay, let's actually iterate over the training loader just for the first batch. So we break here just to make sure that the features look okay. So we have a batch of 32 training examples with a feature size of 10,000 as we expected. So now we can implement our classifier. Yeah, so for this classifier, let's just go simple and use a simple logistic regression classifier. You're welcome to try other classifiers, but you will find that you will probably overfit if you use anything more complicated than logistic regression. So we will define the number of features and number of classes depending on the data set. So we leave that as a argument here. So we only need one layer. Where we define the number of features as the number of inputs and the number of classes as the number of output nodes. Then, of course, our forward method, where we return the logits, calling the linear layer. And then we instantiate the model. So in our case, we have 10,000 features and we have 2 classes because it's a binary classification dataset. We could technically only use one output node. So we talked about that in the logistic regression lecture, but just to keep the implementation more flexible, I like to use it like this, where we, even if we have a binary problem, we use 2 classes, because then if we have a dataset with more than 2 classes, it would also work without having to adjust the code. We could then, let's say, use 10 classes and so forth. So I like this approach where we don't have to change anything here. Oops, yeah, I don't know what I did here. And of course, I forgot the parentheses here too. Yeah, that's usually the curse of talking and coding at the same time. I always forget something. Let's also use callbacks. So we're gonna use a model checkpoint here to save the best model, like we usually do. And then we can instantiate our lightning model. So the lightning model here would be using the PyTorch model, and let's use a learning rate of 0.05. I found this is a good learning rate for this type of model, but again, a hyperparameter that you can experiment with. Yeah, lastly, our trainer. There's nothing new here. I should also say the lightning model, by the way, is the same lightning model we used before. So if I show you the local utilities here, it's a lightning model. Yeah, that is exactly the same model that we used in the previous units. So nothing new here, a very simple lightning model, which is, yeah, what's so nice about lightning models, we can just reuse them. Yeah, and this is it essentially. The last thing we need is the training. So we then just call trainer.fit. We use our lightning model. Let's maybe have a few more lines here so it's not so crowded. A training data loader and a validation data loader, and then we will fit this model. So it's only going to be for 30 epochs, so it shouldn't take that long. All right, we reached our 30 epochs. So the last thing would be essentially just to visualize the results. So we are going to use our familiar plot_csv logger function here and plot the results. And yeah, as we can see, the training loss goes down, the validation loss goes up. So at that point, it maybe starts overfitting. There's actually quite some overfitting, but it is training. So looking at the performance of the accuracy here, we can see also the accuracy of the training set improves by a lot. It's almost approaching 100%. So training longer would maybe be reaching the 100% here, but it doesn't help us because the validation set performance goes down. So we have quite some overfitting here. So you might try to use, let's say, the AdamW optimizer that we introduced in the exercises in unit 6, or other techniques to prevent overfitting. But overall, yeah, this is actually a pretty good baseline. We have about, I would say, 89% validation set accuracy here. So let's take a look at the test set accuracy as well. So we will use the trainer.test here on the test loader, and we will get 88.1%, which is a good baseline. So personally, I always recommend using a simple baseline like this logistic regression classifier and a back of words model before you train any, let's say, more complicated classifier. For example, the transformers that we are going to train later. It's always a good thing to establish baselines. So in this video, we saw how we can train a classifier using back of words features. In the next videos, we will talk more about sequence models.